Before we go ahead with understanding the data preparation part of machine learning, let's try to understand some basic terms which are under statistics so that we are able to use them while preparing our data. Statistics can be broadly subdivided into two categories. One is descriptive statistics and the second one is inferential statistics. To get an understanding of what statistics is and why we use it, let's do a quick experiment. Let's flip a coin. Now, when you flip a coin, you must have already known that the probability of getting a heads and a tail is equal. That is, there is a 50% chance of getting a head and there is another 50% chance of getting a tail. So, there is an equal probability of getting a head and a tail. Now, let's do the experiment and flip the coin once. You will get either a head or a tails. Now, let's say I get a heads. So now if I try to find out the probability from this given observation, the probability of getting head would be 1 divided by the total number of possible outcomes, which was 2. So it will be 1 by 2. Now let's say I do the experiment 100 times. So the number of getting the probabilities, basically if you get 100 heads and tails, so you will have, let's say, around 40 heads and let's say you get around 60 tails. Now if you try to find out the probability of getting a heads, it would be 40 divided by 100. That is not 50%. If I try to find out the probability of getting tails, this would be 60% in this case. Let's repeat it. Now let us take 1000 samples. Out of these 1000 samples, let's say I get around 550 tails. So the probability of getting tails would be 55% and the one of getting heads would be 45%. Now as you see, when the number of samples increase, the chances or the probability of getting a 100 uh, of getting the exact 50% is also increasing. So let's say if I do the experiment 100,000 times. Now in this case, the probability would be much closer to 50% in comparison to the probability when we were doing the experiment only 50 times or 10 times or 100 times. This means the more the number of experiments or the more the number of samples you take, the more near or closer the sample becomes to the population. Now, we did talk about this sample and population, but what is actually sample and population? Okay, let's see this. Population is the entire data set on which you are conducting an experiment. So let's say I'm trying to find out the probability of students passing in a class, then the population will be all the students of the class. And what would be a sample? Sample could be just a subset of the entire class. Now, the main problem here is the sample needs to be a good representative of the population. Let's say the average percentage of the scores which my students are getting in my class is, say, 80%. But when I am choosing the sample, I choose only the top 10 students of my class and calculate the average score for them. Now, these top 10 students would obviously have higher scores in comparison to all the students which are present in my class, because all the students would be having scores which would be ranging from 0 to 100. But here, my sample, which is an not a representative of my population, is having only the top scorers of my class. So these top scorers would obviously be having a high scores. So the average would again be high. So now in comparison to my population, my sample is having an average score of, say, 98%. Now here comes the confusion. The problem is my sample is not an exact representation of my population. Hence, it is very important to basically find out a sample or take out a sample which is in representative of my population, which would only be possible if I take a random sample instead of picking only the top students or the middle students or the low scoring students. I need to find out a sample which is just randomly selecting the students out of my population. The values associated with population are called parameters, while the values associated with the sample are called statistics. So when we say mean, then the population mean is actually a parameter, while the sample mean is a statistics. Now let's get forward to the next topic, which is descriptive statistics. Descriptive statistics are brief descriptive coefficients that summarize a given data set. These are basically the numbers or the estimates, the values which are associated with some data set. Statistics, please remember, associated with the samples, and parameters are always associated with the population. Hence, descriptive statistics are different values which represent the sample. Now, descriptive statistics are broken down into different measures of central tendency and measures of variability. Measures of central tendency are basically the values which tell us about where the center of our data set lies, while the measures of variability tell us about how different values of the data set are different from each other, right? How far away spread out they are. All these details are given out by the measures of variability. The measures of central tendency are mean, median, and mode, while the measures of variability are maximum, minimum, range, quartiles, variance, and standard deviation. We will learn about these measures of central tendencies and measures of variabilities in a while. But before that, let us try to understand descriptive statistics in depth. Now, descriptive statistics are your measures of variability and measures of central tendency. So what are the pros and cons of these statistics, of these particular values? So when we talk about the pros are that it summarizes the data in a meaningful way. So basically when you're trying to get some insight about your data on a top level, It is well done by descriptive statistics. So it will tell you about the mean, it will tell you about the median, the mode, how spread out the values are. All those details will be given out by descriptive statistics. But by using descriptive statistics, you will not be able to draw any conclusions about the data. So that is the cons of your descriptive statistics. So it's very well defined to summarize the data, but it will not be helpful to generalize and create conclusions from your data. Now, the thing is that population is intangible. So population could be very large, population could be something which could be ranging to infinity. When we talk about the world population, then the data about this world population could be infinite, right? But when we will be finding out the details about the population, so instead of considering the parameters like the average age of the entire world population, that would be pretty much difficult to find out, right? We cannot estimate the parameters. So what we do is we actually use the sample statistics, basically the values associated with the samples to estimate the population. Here comes the same thing which I told you earlier, that the sample statistics would be able to correctly estimate your population parameters if and only if your sample is a proper subset of your population and is a proper representative of your population. If your sample is not a representative of your entire population, then the sample statistics which you would be using to estimate the population parameters would be completely wrong and it will give you incorrect results. So it is always advised to basically find out a proper subset, a good representative of your population as your samples. Now, to find out parameters, one would have to find samples and estimate values using statistics, which is called inferential statistics. So descriptive statistics is what basically summarizes your data, and inferential statistics is basically the way of finding out your parameters using your sample statistics. How you find out about your population parameters using your samples or derive conclusions about your population using samples is called your inferential statistics. You can remember it by the word inference. You're trying to infer something out of your samples about your population. Now, when we say representative sample, so it means a proper subset of population, something which could be a good definition, a good subset, a random subset of your population. Basically, what I mean here is, say I have a class of 100 students and I am trying to take out a sample of 30 students. So what I would need to do is I would have to randomly pick the students from that entire class of 100 students. I cannot subdivide the class into different groups and then pick people. I will have to find out these sample representatives, the people who would be a part of my sample, completely in a random fashion, so that there is a chance of every student being selected. There should never be an entity which cannot be selected while you are randomly creating a subset. What is bias error? Bias error is estimations either always overshoot or always undershoot. So basically, when you are taking out your estimations from your sample statistics about your population parameters, if your estimations always overshoot or if your estimations always undershoot, that is the scenario which is related to bias error. This is what bias error is. And what is variance error? Variance error is basically neither an overshooting nor an always undershooting. It will be a mix of both. So it would either overshoot at some time or it would undershoot at some time. So it will randomly vary. So it will just keep changing and deviating from the exact value, but it will not show a specific trend like in case of bias error. Now let's try to understand these different values. Now, what is mode? Mode is the value that appears most often in a set of data. So let's say I have a list of numbers and all the numbers are appearing only once, but there is one number which appears say 3 times and another number which appears say 5 times. So the number which is appearing the most number of times, that is one which is appearing 5 times, would be my mode. What is range? Range is basically the difference between the lowest value and the highest value, that is the difference between your minimum and the maximum value. What is a median? Median is basically the central value which is picked when your data is arranged in an ordered list from lowest to highest. So this is one thing to take care of while finding median. You cannot pick from a data set which is not in ordered format. It needs to be ordered. It should be in some way like 1, 2, 3, 4, 5, 6, 7, 8, so that you will find out the centralmost value, which could be your median. And let's say you have odd number of values. So if you have a data set with odd number of values, then it will be very easy to find out the central value. But let's say if you have even number of values, then there would be two central values. So in that case, you will basically take an average of those two values. Basically, you will add both of those values and divide it by 2 to find out your median. Then what is mean? Mean is the total of all the values divided by the number of values. So say if I have 20 values, so I will take a sum of all the 20 values and divide it by 20, and that would be the mean of those values. Let's see this with this particular example. So here I have even number of values. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 values in total, right? So what is the minimum value? And these are all in a increasing order, right? So the minimum value is the smallest value, which is 1. The maximum value is 100. The range will be the maximum value minus the minimum value. So when we subtract 1 from 100, we would get 99, which would be the range. What is mode? Mode is the maximum occurring value, right? So out of all of these values, if you see 5 is the only value which is occurring more number of times, so it will be 5. What is median? Median is the middle value. So 1, 2, 3, 4, 5, 6. And here we have 1, 2, 3, 4, 5, 6. So this 5 and 6 are the middle values. But median can only be a single value, right? So how would you find that single value? You will basically add both of this. So 5 plus 6 is 11. Divided by 2 will give us 5.5. What is mean? Mean is basically sum of all of these values divided by the number of values. So it will be sum of all of these values divided by 12 gives us 13.5. Now, if you notice, all of these values, the major values are ranging from 1 to 12, right? And the middle value, the median value is 5.5 for us. But still, the mean comes out to be 13.5. That is because we are having this term 100 here. If we would have had 12, then the value would have been much smaller for mean. You can see that in the very next example. So here we have 12 values and the mean for these 12 values come out to be 13.5 because we have one large number 100 present. In this particular example, we have odd values. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11 values in total. For this, minimum value is 1, maximum is 12, range is 12 minus 1, 11. Mode will be the maximum occurring value, which is 5. Median will be the middle value. So because we have 11 values, the sixth value would be the middle value. So we have 1, 2, 3, 4, 5, 6, which is 5 as the middle value, which is the median. Mean would be sum of all the values divided by 11, which is 5.63. If we compare this to the even values, we had only 100 as one extra value in this particular case. But if you see, the mean for this particular scenario is 13.5, while the mean for the odd value scenario where only one value is missing, the mean is 5.63. Hence, just adding one single value which is far away from our data causes a lot of change in the mean. Hence, mean is good to use for average data, but it will not be sufficient to show how the data is spread out. So, if we want to find out how distant different values are, how different values we have in our data set, mean would not be a sufficient entity. Hence, we will work with variance and standard deviation. But before knowing that, before trying to get to that, we will learn about the quartiles, interquartile range, and outliers. Now this table has 13 rows, so it will follow the rules of odd numbers. Now, if you are trying to find out the quartiles, quartiles are basically the checkpoints or the distribution divided into 25% each. So if you consider this particular data set, so 13, for 13 the middlemost value would be the seventh value, which is 87. So 87 will be your median. When we check for the upper half, this upper half is basically the 50% of your data, and the below half is again the other 50% of your data. Now, if you subdivided the upper half again into 50%, then you will get your 25 percentile. So, we had 6 rows. So, when we divide these 6 rows into 2 parts, we will get 3 rows each. So, the top 3 rows are your 25 percentile. The top 6 rows is a checkpoint of your 50 percentile. Then the top 10 rows are a checkpoint for your 75 percentile, and this is a whole. So you know now what first 25 percentile is, 50 percentile is, and 75 percentile is. We can say that 25 percentile is our first quarter, which is 1/4 of our entire data set. The 50 percentile is your second quarter. Basically, first quarter plus second quarter is the half of it. Then you have the checkpoint of your third quartile, which is up to 75 percentile of your data. Out of this, if you want to find out the interquartile range, it will be Q3 minus your Q2. So Q3 minus Q1 will be 119 minus 31, which is 88. So this will come out to be your interquartile range. Now, why is this interquartile range so important? Basically, if you plot a box plot from this entire data, let's assume this data set where we have the minimum value at 3.5 and we have the 25 percentile, which is represented by this particular line at 7. The middle line of this box defines the median, which is your 50th percentile, that is your Q2. This particular line defines your 75 percentile, that is your Q3, and these are the whiskers out of it. So the values before 7 are your 25 percentile values, and the values after 9 are your above 75 percentile values. What is an interquartile range? Interquartile range could be the range between your quartile 3 and quartile 1. So basically Q3 minus Q1 will be your interquartile range. So if you see, your first quartile is Q1 at 7, second quartile is 8.5, third quartile is 9, interquartile range is Q3 minus Q1, which is 2. Now, if you want to find out the lower whisker, it is 1.5 times your interquartile range, which is Q minus, which is Q1 minus your 1.5 interquartile range, which is 4. Then the upper whisker is 1.5 interquartile range plus Q3. So Q3 plus 1.5 interquartile range. So this point and this point is the maximum and the minimum value, which is expected value. Any value which is outside these whiskers is considered to be an outlier. So basically, outlier is a value which is a part of the data set but is an exceptional case. So let's say we have a particular class where all my students are of age 14 and 15. And let's say due to some specific circumstances, a student of age 8 or a student of age 35 comes to my class. So this particular student whose age is 35 would be an outlier. It would be an exceptional case. But when we are trying to find out the details, when we are trying to estimate the values, when we are trying to find out about our population, in that case, these outliers are merely considered extra values, some noise values, values which cannot be considered in your data as they would add some kind of changes in your values and it would cause errors in your predictions. So that is why we need to find out what our outliers are. So this is how you will find out your outliers.
So you will find out what your Q1 is, you will find out what Q3 is, then you will subtract 1.5 times your interquartile range from it to find out the lower outliers. And the values above Q3 plus 1.5 times interquartile range would be your higher outliers, right? So these are the values which you will have to get rid of, or you can maybe take mean or median of the values which are present in your data set apart from your outliers to basically impute values in your data set. But we will talk about it later. We will learn about it while we will be discussing data transformation. For now, this is the formula for interquartile range and finding out the outliers.
As we saw earlier, mean is not a good measure to capture the spread of data. That is because mean is highly impacted by the marginal values. If we have a lot of outliers, if we have a large span of data, then our mean would vary a lot just by addition or removal of one single value also. Hence, we need something which would be able to capture the spread of data properly. We could have done that by taking the distances of different points from the starting point or the ending point. But in that case, the outliers will again pitch in and cause the same issue which was being caused while we were discussing means. Now, the new variation of this is variance. Variance is basically the average of squared distances from the mean. We are taking the square difference of the mean. It basically allows us to capture the distance properly. If we would have taken the absolute distances or directly added the distances, in that case the positive and negative distances would have cancelled out each other and given us 0 as a result. If there would have been absolute values, then the values could have been impacted and there could have been similar results for different distances, and yet the spread would not have been impactful in nature. We will see that in future, but for now, please keep in mind that variance is able to capture the distances properly. The formula for variance is sigma square for population and S square for sample. It is found out by summing the distances of all the points from the mean of the particular data set, square of that value divided by n, which is the number of values that we have. In case of sample, we have same formula where each data point subtracts the mean of the sample and is squared and added together divided by the sample size minus 1. Here you would notice this minus 1 is additional to the formula in comparison to the population formula of it. This is called Bessel's correction. It has been introduced to increase the variance in comparison to population, because when we are taking samples, the variance gets reduced and the distances get reduced in comparison to the population, because we might be missing one or two values in comparison to the population while we are taking the sample, so the variance would automatically be less in the sample in comparison to the population. Basically get rid of this particular difference, we add a minus 1 in the denominator for the sample, which would in turn increase the sample's standard deviation and sample's variance. The formula for standard deviation is square root of variance, which basically allows us to have a metric which is in same units as all other metrics. Here is the formula for standard deviation, which is under root of variance. Here you can see different derivations of standard deviations. If we simply add differences from the mean, then the negatives cancel the positives. So we get 0 here. This would not work. So let's try absolute values. If we take absolute values, the sum would give us 4 here. But let's try another case. In this particular case, the distances of data points from the mean are different from the one above. Here the distances are +4, +4 and -4, -4. This sums up to be 8 and this sums up to be -8. In another example, we have +7 and +1, which sums up to +8, -6 and -2 sums up to -8. Although the values for the summation are similar in both these cases, but if you notice, the spread of data is more in the case below, while in comparison to the spread of data above. Hence, we are not able to find out a particular measure which would give you a good difference between any different scenarios. If you considered squaring each of the difference, then if you see, for this particular case we get 4 as a result, but in this particular case we get 4.74 as a result by squaring the values inside. Hence, we are able to find out a better value, a larger value for a higher spread of data. Hence, this seems to be a better and a bigger value to be used. Here, the standard deviation is bigger when the differences are more spread out. That is exactly what we wanted.